Okay, so we'll get started. Welcome to lecture 15. We've got two pieces left to the class, and that's going to be, various aspects of post-training. Up until now, we focused very much on the big pre-training systems, data, components, and then now we're going to take the big pre-trained model and we're going to make it useful and safe in various ways. So that's going to be the next two lectures from me. Today is going to be RLHF and sort of safety alignment stuff. And then Thursday is going to be RL from verifiable rewards. So things like reasoning training and math and so on will be on Thursday. As I said before, today we're going to shift from pre-training to post-training. Percy in the very last lecture did cover some stuff about post-training data. But really, I think, the focus today is going to be in going from, essentially this big transition that we saw in the field, right? So we have GPT-3, really remarkable system, really impressive, lots of pre-training, lots of compute, but this is not really a useful system, right? I guess there was a couple startups around, building ad copy and things like that, but it was not very useful. It didn't follow instructions. It didn't, do anything particularly too interesting from a product point of view. And then all of a sudden, we got ChatGPT, and ChatGPT can do all sorts of amazing things and follow instructions, and we've kind of seen what that has done to society since then, right? So today's focus is going to be on this arrow right here. Like, how do we take a pre-trained system like GPT-3, and how do we make something like ChatGPT? And then we're going to try to get to the nuts and bolts of that process. And I think most of you, have never, worked on things like controllable generation or like the previous generation of text generation systems. But really, like, modern instruction following models are just amazing, right? Like, this is one of my favorite examples from Sebastian Bubeck's Sparks of AGI paper in 2023, around when GPT-4 came out. But it can follow this like very long block of like nested compound instructions, and then combine that with its coding capability to output zero-shot matplotlib code. And I think all of you just like take this for granted now. It's like, yes, of course ChatGPT can follow 10 instructions at once. But it's just kind of amazing that it can do this, right? And I think part of my excitement about this lecture is the fact that it can do all of this. And the other thing that I think is very important, right, is that now that these systems are out in the wild, safety and content moderation just becomes really important, right? Safety from the perspective of, these models might get misused, someone might try to use them for scams, and also content moderation if you're thinking about this being like useful products that you can like ship and like people would pay for, right? Like, people don't really want to pay for or put ads on systems that are like horrifically toxic, right? Like, I think one of the big reasons why ChatGPT has been so successful is that it has really significant guardrails around it. So okay, given that, the goal today is to try to enable much tighter, better controls on language models, right? Pre-training, you can think of the mental model can be that it packs the model with all sorts of capabilities, right? Like, after pre-training, the model is able to, somewhere within the parameters, do lots of things like reason and answer questions, but it's not going to do them out of the box. And so today what we're going to try to do is get models to do that out of the box. And so what we're going to do is to collect data of various kinds of behaviors that we do want from the language model, and train it to do those things, right? And so the questions that you should be asking now is, what does that data look like? How hard is it to collect that data? Percy has touched on it a little bit, but given the importance of the data, I'm going to re-emphasize it a little bit. I'm going to have some interactive, some exercises to go over that. And then there's algorithmic questions, like how do we make use of that data, right? Certain kinds of data are easy to use, like if you have expert demonstrations, you just train to imitate that. But if you have things like pairwise feedback, like model output A is better than model output B, how do we make use of that? And then finally, like how do we scale this up? How do we do the usual things that we've been doing in this class? So the structure of this lecture is roughly going to mirror the InstructGPT paper, because a lot of the post-training pipeline that we have today is still off the InstructGPT paper. And so the first part of this lecture is going to be on supervised fine-tuning. So if you look at the InstructGPT paper, you'll see this diagram that roughly describes a 3-step process for building an instruction-following model. So part one of this lecture is going to be the leftmost part, the part where what we're going to do is we're going to do supervised fine-tuning on expert demonstration. And then part two, we're going to follow the next two parts of this structure. We're going to talk about reinforcement learning and pairwise feedback. Broadly, I'm going to say that the ingredients in order to get this first part working, I mean, there's two things that we have to kind of think about. The first part is the training data, right? If you're going to imitate expert demonstrations, you better have expert demonstrations. Like, what does that look like? And then the second thing I want to talk about is kind of the method. Like, you have data now. Like, how are you going to adapt to it? And there's an obvious answer. I'll talk about this again, but like just do gradient descent. But there's also a kind of non-obvious part to this answer. And in case you haven't been following how people build these models today, this might be still surprising. So I'll leave that as a teaser for later. So okay. So in Percy's lecture, he's mentioned already several different kinds of instruction data. But today we're going to like walk through a couple of them, and we're going to do a little bit of an interactive exercise. So those of you who have your laptops open can use those for good. So I want to talk about two different details. Like one of them is what's inside these data sets. People often say data matters a lot. I think post-training is one place where this is even more true than before. Because you're using very small amounts of data to get exactly the behaviors you want. So if you have noisy instruction tuning data, you're going to get some pretty crazy behavior out of your models. And then what kinds of things should we be paying attention to? If you're in charge of post-training data collection, what kinds of things might matter? So I have taken 3 different data sets from basically constructed in 3 very different ways. Like you might even call them like kind of 3 different paradigms to building instruction following or post-training data. And we're going to go through each one, and then we'll look at them closely, and then we'll think a little bit about what's going on with these data sets. Okay? So I'm going to talk about Flan. This is by a bunch of Google folks. And Flan is going to be essentially constructed by aggregating a bunch of training data sets from NLP tasks, right? So if you look at it, you see all sorts of different tasks like, natural instructions v2, which has a bunch of, question answering and things. It's got T0 SF, adversarial QA and like topic classification. So basically, this was constructed by taking existing NLP data sets that do all sorts of individual tasks and then aggregating them into one big metadata set, right? So this is one approach to building such data sets. We've got Open Assistant on the right. And this was, I think, a pretty unique sort of endeavor in which a bunch of online enthusiasts got together and decided to write instruction tuning data for language models. Like right after the release of ChatGPT, I think the excitement for this kind of thing was really high. And so there's actually a lot of good, high-quality human-written data from that effort. And lastly, of course, this is a bit of self-advertisement here, but as a representative of the kind of like language model generated post-training data or like AI feedback style data, I'm going to talk a little bit about some of the data from Stanford Alpaca. So let's just look at examples, right? Like I think looking at examples and talking about them are very useful. Now this is from random examples taken from the Flan data set, and you can kind of see the types of stuff that are in here. So, you've got things that look like pretty normal instruction tuning data, like write highlights for this article. Sauntering down leafy avenues past Dutch step gabled buildings, ... And then, in the end, there's even like more information on travel in the Netherlands at www.holland.com. And then it answers, the least known of the Dutch cities, The Hague, was a village, ... And then it sort of summarizes, this as a highlight. You've got something like this. Where this is like, what is this text about? Here are your 4 options. It's business, right? So this is kind of a multiple choice training thing that's happening. This, Percy talked about the Enron data set, so you all can like, smile a little bit. But things like this of taking, let's say maybe the Enron email data set, and you paste back, write a subject line for this email, and now you've got kind of supervision for that task, right? This one. I guess no one here has probably worked on text generation, but this is from a data set called E2E, where you have like a database entry, and then you're supposed to write a sentence that describes that restaurant. So immediately you kind of see you can probably get a lot of data for free this way, right? There's a lot of NLP training data sets, and you can like put them all together, and you will get a really big aggregated data set. And so in that sense, FLAN was ahead of its time and produced a ton of data for this kind of thing. But also we see in many ways that this can be somewhat unnatural, right? Like we've already seen that like this Enron data set is a little bit weird. We can really definitely see things like, oh, here's a text, and then now you sort of append sort of the options to turn it into a task. And so you can kind of see the surgery that you have to do very visibly in order to make this kind of data set. And I think if you look at this, you'll agree with me that this isn't your usual chat interaction, right, for something like ChatGPT. Another example for this is Alpaca. This was like a really, really early attempt at using language models to generate instruction tuning data. And so, just to describe the procedure here, a language model was used. There was a seed set of human written instructions, and then the language model was used to essentially generate more instructions. So that's the left column. And then you use something like instruct GPT to essentially fill in the response, right? And so here, now we have something that looks a little bit more like, on the left, standard sort of ChatGPT inputs. If you compare this to something on the left, this is a very benchmark-centric set of tasks. This feels a lot more like a set of interactions that someone might just throw into a chatbot. And the response is almost always in long-form natural language, versus with FLAN, often it can be quite short, like one word or a phrase or something like that, right? So we kind of see that. Of course, we also see that on the left, these are in some ways not very diverse inputs. They're very short instructions. And then Open Assistant is kind of the third leg of this instruction tuning saga. You kind of see more complex queries on the left. And then because back then, I guess people were just really into writing long, detailed supervision for models, you see like actually really detailed responses. And this one even has a citation on how, like what makes this answer correct, right? And so, very high quality, but also kind of very difficult. And so now this is the first interactive task in this class, but especially those of you that have your laptops open, please go to this URL. This should be a Google form, and there will be a sort of one sort of prompt, and now we're collectively going to crowdsource a instruction tuning response, and I'll give you all, let's say, 5 minutes to do so. Let me know if the link is wrong, but I did test this last night, so hopefully this is working. And then we'll look at the responses briefly, and then I want to talk about why I did this exercise. There is a teachable moment here, rather than sort of getting you just off your laptops for a moment. Okay, excellent. I think there's a decent number of responses, so I'm gonna maybe put them up. Let's see if I can put them up. And then, yeah, there we go. Okay. So in many ways, I think this reflects the kinds of data you get. I mean, if anything, you guys are all motivated to do this task, then I think the standard crowd worker, but you've got the person. I mean, I'm not sure what's going on here, but this is probably ChatGPT. There's a lot of emojis. I'm getting trolled, but this is, I am preparing for liftoff. That's a good response. You've got, the NAFAM, which, of course, is the kinds of things that you'll get out of crowdsourcing. And I think hopefully one thing that you've seen or like felt as you were doing this is that it's actually really difficult to write long-form responses, right? Especially for something that you aren't prepared for, right? And so, you get a lot of short responses like this. It's very difficult, I think, to get people to write sort of long, detailed, responses like this one at the very top. Often those kinds of things are, from ChatGPT. And of course, you'll get things like, I saw this one. Ice cream is a frozen dessert typically made from milk or cream. And you're going to have to, filter out those kinds of things that you're going to get through crowdsourcing. So why did I talk about this? Well, of course, now you have a sense of what this task is like. Annotators in the wild, even if they're experts, will be under time constraints. And I think one of the reasons why, things like AI feedback or using LMs to try to refine or generate these kinds of data has really gotten popular is, if you look at the GPT-4o response to this, it's pretty good. It's a pretty good response to this question. It's very long. It's very detailed. And generating this kind of a human response is going to take a lot of effort and a lot of cost, right? And so you have to, if you're in charge of human data collection at one of these labs, you have to think about, okay, like how do we take, what I showed you in the spreadsheet and incentivize people to generate something that looks like this instead? That is no easy task at all. That is a very difficult crowdsourcing task. Okay, and so these things that we've just seen, they vary quite a bit in things like length. We saw, the ChatGPTism, which is bullet points, like lots of style variations. We saw in the Open Assistant example that, sometimes people put in references. Sometimes they put in sort of very complex, deep knowledge. Like, is that good or bad? I'll talk about that in a moment. And there's also other important aspects to this process, right? Like maybe you want to collect a ton of data or very little data that's high quality, so you got this trade-off. You also have to think a lot about safety, right? Like the data that we collected just now, that's just capabilities data, right? It just makes models answer things like what is CS336. It does not help us make our models, refuse malicious instructions and things like that. So we have to think a little bit about what that kind of data looks like too. Okay. I think length has always been a big kind of gorilla in the room issue for all of these data sets. When back in 2023, when it was very, very popular to generate these kinds of instruction tuning data sets, there's a survey like Yizhang Wang and others at UW came up with this very nice survey looking over the many different kinds of data sets that were created early in that year. And you kind of see, if you look at the length of both the prompts, so that's the inputs, and the responses, the completions, you see like really different lengths of both inputs and outputs. And inputs are probably a measure of sort of complexity of the task in many ways. And then the outputs are in some sense a measure of how much you push the annotators or if you used AI-generated responses. And one of the things that you should be all aware of, let's say you got put in charge of making a new language model, you're in charge of post-training. Well, if you're using human evals, people have a strong preference for lists. I mean, so do actually, if you use AI as a judge, they also have a strong preference for lists. And people have a very long preference for outputs, like 60, 70%-ish preference for longer outputs. And so do sort of AI judges, right? And so this is a little concerning because you want to be optimizing for not just kind of the stylistic content of your responses. You ideally want to be using post-training to do things like reduce hallucinations and actually make the model hopefully more capable. One thing that we do see is that these factors are not super relevant for benchmark performance. So if you look at, for example, MMLU performance, kind of despite the really big variation in length for a lot of these models, most of the instruction tuning data sets, like the simple ones, give you boosts over kind of the base model, which is the very top row above. So I think one of the things that I'll say here is, chat style evaluations have their place. Chatbot Arena, Alpaca eval, these kinds of automated, evals have their place in helping understand like user engagement and things like this. But benchmarks also have a very important place because when you post-train, you don't necessarily want to be too affected by, for example, length biases and open-ended domains and so on. And so you want to be really careful of these effects. You want to have a diverse array of evaluation strategies to try to avoid those pitfalls. One other thing that I think really trips people up when they initially start thinking about these things is to say, oh, what I'm doing is I want to collect high-quality data, and high-quality data has lots of deep knowledge and has lots of citations, right? Like that's a reasonable thing to say. And I think Open Assistant I think had a great example of this, right? And so here's an example input-output pair. You've got a introduction about monopsony in economics, and then there's these references on the response on the right. So now, let's say we have a model, and we fine-tune the model to take the left side as input and reproduce the right side as output, right? So you can kind of think about two different things that this process is going to do at the same time. Right? So one of the things that this is going to do is it's going to associate, monopsony with that citation, right? So it's learning new knowledge. So that is good, right? So that is a positive thing to do. But it's also going to do a second thing at the same time, which is this kind of generalized thing of saying, if you ask me a complicated concept, I had better finish the output with a reference, right? And so it's basically the first thing is teaching new knowledge, which is good, but the second thing here is kind of teaching the model to hallucinate, right? Like if the model doesn't already have somewhere within its parameters an association between monopsony and this citation, this Bivens and Mischel book, what might happen instead is it just learns that, oh, what I should do is whenever I have a complicated input, I should give a response and then make up a reference at the very end, right? Those are two competing explanations for what is happening here. And this is going to motivate, in some ways, the second part of this lecture, right? John Schulman has this kind of great talk. I think he gave it at Berkeley, where his argument is basically if you do this kind of thing, you're going to encourage the model to hallucinate, right? Like the model doesn't have the knowledge of answering a question. You force it to answer that question. What it's going to learn is, of course, it'll learn the knowledge in some abstract sense, but it will also learn the other aspect of, I just need to make something up in order to sort of type check what the response should look like. Okay, yes, there's a question.
Writing has a sense of like, okay, I think I need to add a citation here. Let me search for the relevant citation, either from memory or let me actually use a database. It is the fact that like the LLM is learning that like, okay, here I should insert a citation is actually a correct and desirable thing. And the fact that it's a made-up citation is either a memory issue or B, something you can maybe augment a tool usage in the like. But like, I don't see why the behavior of needing to add a citation itself is problematic. With like, if you can either fix the memory issue or the tool usage issue.
Sure. I mean, I think so to repeat the question was like, I guess that was a more comment than a question, was that the learning to put in a citation isn't a bad thing, right? Like, I mean, maybe you augment it with tools and it'll actually give the right citation. I mean, that's a fair point. But I think the thing to maybe point out here is like the deeper conceptual, or not conceptual, the deeper issue with token prediction, right, is that you're teaching the model to kind of predict the right kinds of tokens. And here, essentially the lesser of the two errors is to say hallucinating is less bad for my loss than not making up the reference at all, right? Kind of the structure of the response always has to be fulfilled because you have to fill the tokens in at the right places, right? Of course, at scale, if you know the facts, if you have the right tools, right, those are good. You want to kind of make the predictions on the right spaces. But I do kind of think this is very indicative of this failure mode that models can get into, where you're trying to get it to do things that it can't, right? Like if your SFT data is just much more advanced than what your pre-trained model naturally can do, you run this risk of teaching the model kind of this alternative shortcut behavior instead of teaching models the right behavior. Yeah, so that's John Schulman. I think he makes a fairly reasonable case that this is one of the reasons why like on-policy RL, like reinforcement learning style things, is an important thing to do, because you want to know what the model already knows and only teach it those things to avoid it hallucinating. And whenever it's encountering some fact that it doesn't know, then maybe you should change your fine-tuning data to say, oh, I don't know that fact, instead of forcing the model to try to answer, right? And we kind of see this on the kind of other sort of knowledge storage studies as well, where people have kind of talked about it's much easier for models to sort of reproduce known facts than sort of to learn sort of unknown facts, where it just takes a lot longer for models to kind of learn facts that aren't shown in pre-training. And this sort of is sort of matching what you might expect from these phenomena. So okay. I think one of the things that I'll sort of, summarize that with is that there's a very counterintuitive phenomenon for instruction tuning, which is that, you can have an instruction tuning data set that is fully correct and like actually very rich, but actually that might not be good for your LM, because it's going to teach your language model to sort of try to make up facts to match that depth of knowledge. That's always been, I think, one of the arguments for why you want to be really careful with both distillation data, where the teacher model is stronger than your student model, and also really human annotation, where the human might be much more knowledgeable than the model, right? You want to be really careful to make the model abstain nicely when it doesn't know things. And in principle, reinforcement learning style correctness could help, and we'll talk about that in a moment. And sort of optimizing this at the instruction tuning level is just really messy and very difficult. I don't think people have really nailed it down at least in the open research literature. The other thing I want to talk about briefly, because I think this isn't necessarily something that can be solved with instruction tuning alone, is to touch on safety and to think a little bit about what the trade-offs are here. So we know, language models need some guardrails. They're deployed straight to end users. They're very capable, so they might be used for misinformation or for generating things like scams or spam. And so there's a need for safety tuning these models. And I think in parallel with a lot of the research on instruction tuning, there's been actually quite a bit of work studying safety tuning as well. And I think some of the early work in this area kind of has shown that even a small amount of sort of safety tuning data that's mixed in to instruction tuning process can make models much safer, sort of paralleling a lot of the findings that people had that actually for instruction tuning as well, if you have a strong enough pre-trained model, even a small amount of instruction tuning data can get you a lot of the way. Not to say that's sufficient, but actually that's sort of gets you to a reasonable point. And I think the core trade-off with safety tuning that I'll sort of touch on in this brief section is this trade-off between refusing things and not refusing kind of too much, right? So there's always this thing of, if you have unsafe responses, you want your safety tuned model to just refuse to answer. And then maybe you have these other, actually safe responses, but things that look like unsafe responses, like how can I kill a Python process, right? We all know that is a reasonable question to ask, but I guess if you're not, if you don't understand English very deeply, you're like, oh, killing sounds very dangerous, so maybe I should refuse to answer that question, right? So how can you make models sort of understand this nuance? It's a very tricky thing to do, purely in the instruction tuning setting. And so a lot of what people have done is come up with carefully curated small instruction tuning data sets to try to balance this trade-off. So even some research has shown that even like 500 examples can make models follow some of the safety guidelines well. So okay, to put this together, instruction tuning is surprisingly powerful. I think, you would think that given how powerful things like ChatGPT are, that there's actually a ton of complexity into getting anything that works. I think you'll find that even if you take a fairly standard instruction tuning data set like OpenHermes or OpenAssistant or any of these data sets, and you take a base model and you fine tune on it with reasonable hyperparameters, you'll get a model that behaves a lot like Llama or ChatGPT. It won't be quite as good. There's a lot of extra work you need to do to optimize it, but you can get pretty far. The second thing that's good to remember is basically the notion of high quality data is just very complex, and you have to reason about it really carefully. It's not obvious how to do. And then the last thing is, actually even a small amount of data can have great leverage at this stage in changing how models behave. The last thing I want to end this section on is how to do this instruction tuning. There's kind of a flippant answer to this, which is, well, you've got demonstrations. Just put in the instruction and the response and just do some gradient descent, right? We all know how to do gradient descent at this point. And I think in most academic settings, that's basically it, right? Like you're done. You do your small scale gradient descent and you're done. But I think if you're at like a frontier lab and you've got more compute and you've got more money than you know what to do with, then you've got a lot of compute and you've got a lot of data. And so you can scale this whole process up quite a bit. Like you can scale it up a lot. And modern instruction tuning pipelines are starting to look a lot like pre-training pipelines. And so increasingly, the boundaries between pre-training and instruction tuning are just getting blurred. Because if you think about it, instruction tuning data is still a sequence, right? It's just a sequence of tokens. And so I can throw that into my pre-training process, and that's a totally valid thing to do. And so this is an increasingly popular idea. I think the close labs don't tell us anything, but I think the things that people have tell me in bits and pieces suggest that this is what they're doing. A lot of the open groups from China do basically this now. And so what you do is you have your usual pre-training setting, right? You do pure pre-training. And then what you're going to do is you're going to start mixing in instruction tuning data into pre-training. So the kind of the tail end of your pre-training, especially as you're kind of annealing the learning rate, you're going to start putting in a lot of this higher quality data or instruction tuning data. And then in the end, you might actually do a second short instruction tuning round. But maybe this is smaller because most of your data has already gone into the second stage, what people call mid-training. And this is cool because it lets you scale up without catastrophic forgetting issues. You might get more leverage out of your data because it's integrated more deeply into pre-training. And to give you an example or a sense of what this looks like, it's a bit of a shame that data mixes are often pretty closely guarded secrets by a lot of the groups. So I've taken this figure from Mini CPM, which we've talked about before. Great paper from the Chinese groups, where basically they have a two-stage training pipeline where they have a first stage where they do pure pre-training. And if you look at this pie chart, this is all pre-training data sets. Common Crawl, code pre-training, Pile, Dolma, they've thrown it all into one big pie. And then they have a second stage, which they call the decay stage. And so if you remember my lecture on scaling laws, I talked about WSD, warm-up, stable, decay. So that's the stable stage, that's the decay stage. And in the decay stage, what have we got? We've got Wikipedia, what people might call high quality data. We've got still the pre-training stuff mixed in there, so it's not pure post-training data. But then if you look at the right, we've got code SFT, we've got Chinese books, we've got Ultra Chat, we've got Stack Exchange question answering, and Evil Instruct, and OSS Instruct, and all sorts of other things. So those are all kind of instruction tuning or instruction tuning adjacent data sets that you've thrown in onto the second half of pre-training. And it's, I think, used by most models today. And Mini CPM and other sort of derived LMs that are derived from that lineage of models have definitely sort of publicized this. I think it's extremely effective to do this, and so I think everyone has been following this. One last commentary I'll make before we move on to RLHF here is that this whole process makes it very, very difficult to reason about pre-trained models versus post-trained models, right? If you look at recent releases from like Quen or whatever other companies that you're looking at, and they say base model, that base model is probably at the end of this process, and so it has basically gone through an instruction tuning phase implicitly through its mid-training process. We don't exactly know what the mixes are for a lot of these closed models, but it does actually mean that I think the term base models is increasingly questionable what that really means. So that's my sort of side comment that is useful for you if you're thinking about base models and so on. Yes?
So when you say this is a data mixture you train during the decay stage, like when you have linear data goes to 0, that's when you get like these big heaps of loss. Is that like directly correlated with data it's seen in that last decay stage?
Yeah, so that's right. That was the motivation for a lot of the two-phase training for these groups. Like they basically use essentially the large drop in loss as a way to try to anneal the model into the right mode. I think there's increasing studies into like what's the optimal point at which to switch, and I think it's a little bit more nuanced than that. But I think to first order, this has been a very effective recipe. Yes.
Between blending primarily with catastrophic forgetting, or I was trying to think about the incentivized citation thing from earlier. Does this also have that?
Yeah. So I guess there were two questions packed in one, but the question was like, is this primarily for catastrophic forgetting, and also does this help with the citations issue? So to answer the second part first, I think it doesn't help with the citation issue because just as sort of like a type signature thing, the only things that can help with the citation issue is if you know what facts the model knows, right? So you have to either ensure that the model like always knows the citation facts before you show it the SFT data, or you have to like check to see if the model knows it and then show it that data if it does know it, right? Which this doesn't do. This will always unconditionally put in those data points, whether or not that citation is learned. So it has no way of fixing that adaptively. Catastrophic forgetting wise, I think that is one of the motivations that if you have so much SFT data, your trade-offs are pretty tricky, right? Because unless you're going to do this kind of almost pre-training mixed in with post-training, you have to think about regularization. You have to think about tiny step sizes to avoid messing up your pre-training. And so I think this is partially motivated by sort of catastrophic forgetting adjacent issues. It keeps the model sort of more general. Yes?
With the John Schulman example for hallucination, is that if the model doesn't know the reference that's included in the post-training data that it hallucinates, so if it does know that fact, then it would not have the same behavior?
That's right, or that's the claim, right? That if the model did know, this citation that's right here, then the model wouldn't necessarily, out of these two sort of competing mechanisms, what it would learn is, oh, whenever I see this example, I should retrieve, my knowledge about, Bivens and Michel L, and then use that as a citation. I think the reality of this is that it's always very complicated, right? Like, what does it mean for a model to know something? How reliably does it know something? And so these two kind of mechanisms are always maybe in superposition for a model. It's really just a question of which one is more dominant. Like, if a model just has no idea about this, it's probably two that is, more dominant. Whereas I think if the model knows it reliably, it's more likely that it's just going to learn the correct citation rather than encouraging broad general hallucinations. Yes?
Tried putting into all of the pre-data some kind of thought tokens that tell the model, oh, this looks like a fact, let me check if I actually know it. And so I'm going to query myself, and check if I'm giving consistent answers, and if so, I'll print out. Right? So that in the entire pre-training process, it has a thought process of I need to check myself.
Okay, that is a very interesting idea. So just to repeat it, it's has anyone done something where you put in like kind of thought tokens where the model's checking itself for its knowledge of facts as it trains or something like that, right? Is that roughly right? Yeah. So depending on how you interpret or like implement that exact idea, it starts to look a lot like reinforcement learning. Because, for example, there's a method called Quiet Star from some folks here, Noah Goodman and Eric Zelkman and others have done this, where they do essentially they try to learn the thinking process of a model by sort of predicting what happens on the answer token, and then based on whether or not it's correct, it tries to like reinforce the model to have good thought process. Actually, the even closer analogy to this is STAR, which is the original paper, which is if the model gets something correct, then that thinking process gets fed back into the model training. And if it's wrong, then it doesn't, right? And it's kind of very similar to what you're proposing, which is to adaptively train the model based on kind of correctness of its knowledge or whatever else.
I'm proposing just to give it thought processes that say, let me make use of this tool that checks myself, and I can later at some point change what that tool is. But the point is that tool will come with a response that says, yes, I do have the knowledge, no, I don't. And then you'd actually see that knowledge gets printed out or doesn't, depending on.
I see. So in this like tool use example, are you imagining that kind of the fact would get replaced by a tool call, or will the fact still be there? Like, I think the key question is, do you force the model to predict the fact tokens, or do you just force it to predict, like, use a tool to look it up on Google token?
No. The tool just checks if the model knows it. You don't know what the tool, how you implement it, but you see if the tool says, yes, I do know it, then there will actually be some response printed out in the pre-training data. And if the tool says, no, I don't know it, then the pre-training data will just say, actually, I don't know this, I'm going to skip it. And so...
Right. So I think that's hard because when you do pre-training, like you have to know whether you know the fact to know whether to take losses on that knowledge token, right? Like you can't defer it to inference time, because you have to decide whether or not you're going to take gradient steps, right? And the other sort of logistical difficulty here is during pre-training time, you have a static data set, or for computational reasons, you would want a static data set. And if you have a static data set, you can't adaptively do updates, right? Like anything that solves the hallucination problem has to be kind of reactive of the form, what does the model know? And then do I take updates on this or not? At the pre-training stage, that's very difficult, unless you're doing RL style stuff at pre-training scale, which would get you very close to that, but still very difficult. I'm happy to follow up, but I think hopefully that answers the question. Oh, there's more SF. Yes, okay.
So if I, for example, in case of llama, if in the pre-training data we haven't realized the emoji, But in the country, if we have a lot of the emojis and end up with this, will it cause the effect that when we use that to fine-tune the model and the result model will have a lot of repeating sentences similar to emoji patterns at the end?
Yeah, okay, so the question was if at pre-training we don't see emojis, but at post-training we put in a bunch of emojis at the end, what will happen? It depends on the structure of the emojis, I guess. If the emojis are dependent on the inputs in a very complex way, and that's very difficult to learn, maybe what the model will learn is, well, in post-training, what I saw was a bunch of emojis. I don't have enough data or training to know what the complex pattern is. So the model will just learn to put a bunch of random emojis at the end. If there's no pattern, if there's no complex dependence, then maybe the model will learn to do the right thing, which is just to put a bunch of random emojis at the end. Really, the key way to think about kind of the SFT issues is instruction tuning will reliably teach the style of the output, like the type signature of the output, right? And the model will most likely follow that type signature at the very least. And the real question is, do you have enough instruction tuning data that you could do something more than that? And that's kind of the more complex open question. So in your emoji case, at the very least, you'll get a bunch of emojis. Whether those emojis are the right emojis, open question, right? Depends on how much instruction tuning data, depends on pre-training, so on and so forth. Yes?
I was wondering, like, earlier in the lecture, I think it was said that the post-training part doesn't really teach like all new knowledge, right? It's mostly about the styles. And then like the line kind of gets more blurry, like when we sort of have this like mid-training stage. So and I think you showed like the mini CPM paper. So like in this sort of new like scenario, like the mid-training part could also instill some sort of new kind of like word knowledge into the model.
Yeah, that's right. So I guess the question was like, if I rephrase it, can't instruction tuning essentially teach new world knowledge because mid-training blurs the line between pre-training and instruction tuning, and we know pre-training teaches knowledge, so why not instruction tuning? And I think that's right, that like in some ways instruction tuning, if it's scaled up enough and it's diverse enough, will teach knowledge, right? But I think instruction tuning in its like smaller, like non-mid-training form, it is very difficult to have the scale and diversity of data needed to reliably teach, various facts. I think modern mid-training is starting to become a different game, but it's still sort of an emerging object, I think. Cool. Okay. So now we get to the part 2, right? So part 1, this is the quick intro to instruction tuning and SFT. Now we get to reinforcement learning from human feedback, right? The RL part of this lecture. And conceptually, right, and I'm going to take it slow here because I think this is an important conceptual transition, right? We're going to move from the world of I think, generative modeling at the very top here, which is, there's a very simple goal in this world, which is there's a P star. P star is a reference distribution from which completions are drawn. That reference distribution probably looks like some mixture of internet data as well as annotator written data. But there exists some abstract P star that we're trying to imitate, right? That's all there is to it. So this is pure generative modeling. Now we're going to move to the second perspective now, which is RLHF. And in this world, I no longer care about matching any distribution, right? So probabilistic perspectives kind of don't really entirely go out the window, but you want to be careful about adopting those. Because really what we're looking for is we're really just looking for some policy, P of y given x, such that we maximize our rewards, right? There's some reward function, R of y and x, that take in both my completion and my prompt, and then gives me a reward. And all I'm looking for is any policy that gives me good rewards, right? And so now LMs are not necessarily a model for some underlying distribution. They are policies that give us good rewards. And so why would we go and do RLHF? There are kind of two reasons that we might do this. One of them is on the top one in SFT. In order to do this process of imitation, we have to get samples from P star. And that can be quite expensive, right? And the second one, all we need to do is get measurements of rewards R. And SFT data can just be really, really expensive. This is kind of like a caricature of various costs that you might have in different stages, right? You have some compute costs when you train your base model, and then you're doing like supervised learning, like SFT, and then you're going to go collect a bunch of pairwise feedback and do RL and do evaluation and so on. So when you do this, right, the SFT is just really, really expensive. You're getting like really expert people to write very long form responses. And you kind of saw how annoying and difficult that was. And frontier labs are going to be spending millions on this post-training data. Well, maybe there's a nicer way of collecting data that makes models better. So that's one argument for why we're going to do all the things that we're going to do in the second part of this lecture. There's also a second reason that is equally, or maybe even more important, that I think people do this kind of RL training. And one of the things that's very interesting is, people don't always agree with themselves about what is good. So if you ask somebody to write a summary, they can write one summary. And then you ask them to compare their own summaries to LM-written summaries. There's a good amount of people that will actually prefer LM-written summaries. And this was a really surprising result from one of my students' papers, I guess 2 years back now, where we were benchmarking summarization systems. And there was one person who is, of course, anonymized, but Annotator 1, who wrote a bunch of summaries, and they actually preferred the AI summaries actually significantly more than their own. And they're like a freelance expert writer or something. And we went and interviewed them, and they were like, yeah, when you asked me to write stuff, I just felt like I had to write more with flowery language. But then I read the AI ones, and they just read better. And I'm sure you've had similar experiences, where you look at the output and it is actually different from your own assessment of how to generate. And so there's a not just cheaper to verify than generate, but actually maybe higher quality to verify than to generate. And so there's this generator-validator gap. Okay, so we're going to cover different aspects of this RLHF process. We're going to talk about how we collect data and what are things you should worry about if you're in charge of RLHF data collection. And we're going to talk about how we do RLHF. I'm going to talk about two representative algorithms, PPO and DPO. I'll defer some of the more detailed explanations of PPO to the next lecture, just for kind of space reasons. And then finally, we'll end with some things to worry about, almost like pitfalls of RLHF at the very end here. Okay. So how do we get pairwise feedback, right? So pairwise feedback is, I'll go back here and just take it a little slower. So when we do the second part of this instruct GPT process, right? How does this work? Well, we have the model sort of generate its own outputs, right? These are rollouts in RL terms. And then we're going to compare, these different outputs. And although the 4 outputs are shown here, in kind of standard settings, you often just have a pair of outputs. And let's see, we have A and B. All I want to know is A better than B or not, right? And then given these pairwise feedbacks, I'm going to train a reward model that can essentially internally give every single output a scalar value, and then just use that to do reinforcement learning. This reward model is now my rewards, and I want my model to maximize those rewards, right? Fairly hopefully simple pipeline. So how do we collect pairwise feedback data? Well, the obvious simple thing to do is just say, okay, I'm just going to make some web app. I've got 2 different AI responses, and you're going to have a little, 4-way checkbox that checks which response is better. I took this from one of the studies that we did, right? A lot of pairwise feedback responses look, similar to this. But I thought, one thing that would be helpful and useful into actually getting a sense of what does this look like for real. I have gone and sort of dug up examples of annotation guidelines from different papers and different places, sort of, talking about this process, right? So if we look at the Instruct GPT guideline, this is one of the very few, I would say, sort of released materials from one of these companies describing their annotation guidelines. They say, okay, your job is to evaluate these outputs to ensure that they're helpful, truthful, and harmless, right? So those are their 3 pillars. You've got helpfulness, which is writing in clear language, answer the question they mean to ask, being sensitive to internationality. If someone says football, they shouldn't assume American football. If it's too confusing, ask for clarifications. I want you to be truthful and not hallucinate outputs. And by harmless, you should sort of be not toxic and be very nice and not say NSW things. All fairly reasonable things. But you can kind of see how there's the interplay between things like the model spec, which OpenAI publishes publicly. Then there's a very detailed annotation guideline, which, this is not that detailed. It's probably much bigger in practice, where you would write down these kinds of bullet points. You would hand this to annotators, and then they would sort of go and make annotations. This was, InstructGPT is not even like kind of production grade. This is early days, but you see how this process kind of works. The kind of other interesting example, you can kind of go look this one up later if the actual text is too small, because I'm not going to read through all of it. I'll just sort of touch on it a bit. There's actually a leaked version of the true annotation guideline, apparently, for Google Bard that I think was part of some like news story. And you can kind of see very, very similar things happening here, right? We've got on the top left box, like helpfulness, like you should address the intent of the user's prompt, you should adhere to any requirements, don't have misleading information, like very similar to the InstructGPT setup. We've got actually here a style box, which is, what kinds of style are good or bad. And then we've got, different rating scales for the different responses. And if I remember right, I think the Google Bard folks, I think, gets like a minute per question to be doing this task, which is quite difficult. Okay, and then for InstructGPT, they go through like scale and Upwork, and they collect about data from about 40 people. Like this is really, really tiny, sort of by today's standards, but hopefully you kind of get a sense of what types of groups are being involved here. Okay, so this is the second part of our interactive exercise. Okay, cool. So that's 5 minutes. I guess to take a straw poll, I think about 27 of you managed to complete this, which is great. Thank you for your participation. How many of you managed to fact check all the facts? Yeah. Yeah.
The longer expression is completely factually wrong.
Right. Yes. Yes, that's right. So how many of you managed to fact check, any or all of the facts? You managed to fact check things?
Just one.
Just one. Okay. How many of you managed to check the math in the 5 minutes? Okay. So there are a couple people. Okay. Good. Excellent. Okay. That makes me happy. The point of this exercise, partially, I think maybe you could have guessed what was going to happen here. The shorter ones, most of them are essentially taking the longer ones and actually just removing the hallucinations to the best of my ability. And so for the most part, basically for those of you that picked the longer one are sort of picking the slightly longer but hallucinated ones. Like I don't quite remember which of the pair of games ones that are hallucinated, but many of them are. And so, we see strong disagreement, and actually the longer one gets more votes despite having strong hallucinations. This one, I think, both is correct. So B is probably the better choice. The two math ones, I think you can also back out by the unnaturalness of this construction. The one that's like sort of more conclusive actually is going to the wrong conclusion. This is not mathematically fully correct here. And so, you probably should find it difficult to try to do these judgments this quickly. There are very, very strong challenges in collecting this kind of pairwise feedback at very, very large scales. Just because even though you only have to verify if I'm showing you a math problem or I'm showing you, something like a very, strong, factually laden, text, you're going to have to basically break this down into claims and check each one to know whether one is, wrong and one is right. So this is just like a very labor-intensive and difficult task. And I gave you 5 minutes because essentially I think the news story that the Google Bard article was associated with was basically that the annotators were given 1 minute per example, and there was big complaints that like this is not enough for us to judge the safety and factual accuracy of the model, and you hopefully somewhat agree that it is a very difficult task, right? So okay. The lessons here, going back to the flow of the lecture, right? It's very hard to get high quality verifiable annotators. Like I think you are in many ways like pretty high on the bar of like people that are actually motivated to do this because you're just doing it because I asked you to, not because I'm paying you to or to get grades. It's very difficult to get people to check correctness, especially under time constraints. And the last one, I don't know if those of you are doing this, right? But if you put in an online survey like this, someone's just going to like take the whole thing, dump it into GPT-4, and then just like kind of copy the answers straight back onto your Pairwise responses. We've had several studies in the past where an annotator had like 95+% agreement with GPT-4, and you kind of have to wonder what's going on there. And so it's, despite the fact that pairwise feedback is easier to collect than supervised imitation data, there are still significant issues. And I'd be remiss to not point out, the many things that have been written about sort of the kinds of problems that this creates if you try to outsource this to third world countries. There's sort of pricing concerns and sort of lots of ethical issues that you all should be aware of, if you're sort of going to be in the future, be a part of these kinds of sort of data collection pipelines, right? You want to make sure to get high quality data and to also make sure that, people are being paid kind of living wage. The other thing to be aware of, this is in the sort of bias and safety angle, because for alignment, I think this is a really important thing to also touch on, is that, in some sense, RLHF and alignment come at the end of the pipeline. And because they come at the end of the pipeline, they have very strong influence on model behaviors. One of the papers that actually Percy and my postdoc Shibani and Essen, a postdoc of mine, worked on was this paper on trying to figure out like how do subjective opinions of LMs align with different groups of people. And one of the really interesting patterns that we found was actually for Instruct GPT, like these are old models, but the now still useful models. These models somehow became more aligned with sort of Southeast Asian religions than before. And then we looked in the appendix of Instruct GPT, and actually, like, what's the nationality of the people doing the annotation? It's Filipino and Bangladeshi and 17% American. And I was like, oh, it's kind of surprising, but it does, circumstantial evidence lines up, with this kind of thing. And so you do have to be very careful, because this is the thing that in some sense goes out in ships. Others have also noted that, depending on the annotator, what they pay attention to is very different. I really like this paper from Hosking, Blunsum, and Bartolo, where they basically study, two different kinds of annotators. One is like the authors, and they're like very motivated to like, judge things correctly with quotes, and then crowd workers. And what they really find is, crowd workers don't pay much attention to factuality. That's kind of this row here. They pay more attention to formatting, right? So depending on the annotator, you're kind of getting different kinds of feedback, even though you're asking them the same things, right? And so kind of increasingly, people have turned to, as with the instruction tuning phase, AI feedback or LM-generated feedback. And so there's been many works, including some of our own, that have shown things like, if you try to get pairwise feedback from GPT-4, it has very strong agreement from like GPT-4's estimated win rates of models or responses, and sort of the human estimated ones on the y-axis. Same here. The agreement between human to human, which is the blue box here, is roughly the same as the agreement between GPT-4 and human, but is much cheaper, right? So there's lots of reasons, I think, why sort of AI feedback has become popular. And it has been used very extensively in RLHF. So if you look at ultra feedback, which I think is one of the very popular open source data sets for sort of off-policy RLHF, you see this. If Zephyr 7b, I think, was a Hugging Face effort, I want to say last year, to build a big, strong open model. And the reason why I bring this up, I think Zephyr is probably not the most well-known model, but one of the things I kind of remember about sort of the Hugging Face model process was, initially they were really interested in human data collection. Like they were convinced that like human crowd worker, like if you paid them enough and got the right vendors, would outperform sort of AI-generated feedback. But kind of late in the process, they kind of realized, GPT-4 generated feedback for this kind of thing just worked much better. And so a more modern example of this is Tulu 3, which is a sort of post-training paper/project out of AI2. And they've done kind of roughly this. Like they take different prompts, they have lots of different models to generate responses, and they have, a LM sort of rate these to get chosen versus non-chosen. And this really all just kind of goes back to the classic paper would be the Anthropic paper on constitutional AI, which I think sort of, really planted a flag on the ground in terms of AI feedback being used for this kind of alignment process. Finally, the last thing I want to talk about for data is length effects. I think when we did the annotation, one of the things that we saw was I think many of you saw the longer response, and you're like, this is more detailed. I like details. This is good. It's not just you. Models and people all have this bias, and so people have found that models that people have thought were better were in fact maybe only just also longer, and then AI feedback seems to make models just generally longer. And so this is always a confounder that you want to be careful of, length as a confounder for general preference. Okay, there was a question there.
I'm on off policy and on policy.
Okay, yeah, I'll talk about off versus on policy later. Off policy, I think I mentioned it here, is going to refer to you collect these kind of pairwise feedback things separately. Like they're not collected from the outputs of your model. Maybe your model is involved. Like for example, in Tulu, you've got all these kind of off-policy data on the left. That's models that are not your own, but you also have on-policy data from yourself, right? So the off-policy data kind of tells you about the landscape of places you're not at, and the on-policy data tells you how to refine yourself. Yes?
So, the way the sort of human aspect of this works, we're sampling prompts and then asking humans to grade them. Have people ever, instead of sampling prompts that you don't have the answer to and then asking humans to grade them, you have existing in the world from any number of places, there are existing prompts that we know the answers to, and we have that data saved. We don't need to do anything to receive that data. Have people done sort of alignment tuning using that style of data instead of asking humans or LLMs?
Yes, okay. That's a good question. And it's like, why don't we do RLHF on, or can we do RLHF on domains where we know the answer? Is like one way of putting the question, right? And part of the answer is the next lecture on Thursday is kind of that. Like, where do we really know the answer? Math. We know the answer very well for math, and we can do exactly RL against math, and it works very well. People also do things like, here is a long form response from an expert that has already been written. Now, can you judge it given this? That helps, but one thing that I think is important to keep in mind is for a lot of these open-ended tasks, there's many correct answers. And it's very difficult to judge which are correct. Like if I have a new fact in the LM response, is that a correct fact or not, doesn't really solve those problems. Yes?
So thinking about, for instance, the Anthropic paper you referenced, there's this relatively specific and small constitutional thing, but we can even sample values to make this work for open-ended things, because we have any number of sources of here's a problem, here are values that we as a society think are relevant, whether that's surveys or politics or articles, just any number of sources.
Right.
People do that. I know that Anthropic did let people vote, but that seems small.
Yeah, I guess there's lots of different things being mixed in on that comment. You could do deliberative democracy style stuff to align models. That is certainly a thing. There's also, I guess, the thing that feels close to what you're talking about is almost giving the annotator sources almost that are relevant. And I'm sure those things help. There have been works on showing people expert written responses when they do the pairwise judgment and so on. But I think it's not a silver bullet. All of this kind of UI interventions definitely help, but it's not necessarily going to, in one stroke, solve the problem. Okay, yes?
Just a random question. Is the paper where you have you're using LM to annotate your other LM responses? You know, if there's bias from GPT-4o to its own generation.
Yes. There's a very strong or very detectable self-preference for most models for their own outputs. And so when you use this for evals, which many people, including I, have done, you have to be very careful for that self-bias. Absolutely. Yes. Okay, then there's lots of hands. But yes, I think you were first.
Balancing the amount of information you get just from having a model create its own outputs and then, I guess using the models to do its own feedback, right? Is there a heuristic for how many iterations that you can do, and does that change if you use, say, a sampling of different models from a model itself?
Yeah, I guess the question of how much can you extract out of models doing things to themselves is an interesting question. But I guess the kind of in some ways, the information theoretic bound, so to speak, is very, very high, because technically the model like ingests the entire pre-training corpus, and that could be stored somewhere in the model. And depending on how you prompt it, you might get an amazing model out. And so it's possible that based on how you're using the model as part of your self-refinement loop, you can extract more capabilities out of the model. And we don't know what the upper bound of that is, because basically the inputs are just vast. But I do think there's like practically lots of papers that have studied this question of like how much can self-improvement help, like what's the scaling properties, and so on and so forth. I think ultimately it's a very empirical question. Okay, yes?
I think of the as kind of like a ranking problem, because compared to SFT, so basically SFT is to choose the best answer. We have a label for that. But for RL, we don't assume that we don't have label, but we have like a reward model to give it like preference.
Yes.
So that is kind of like a ranking thing.
Yeah, so maybe I should just go through the next slides, because I think that will actually explain it. So not only does it help us get through the rest of this, hopefully quickly, but also I think it'll explain your question. So okay, so now let's talk about methods. Our goal is to do this thing, right? I want to find a policy to maximize my rewards. So I need to tell you what the rewards are, and I need to tell you what the maximization process is, right? So let's do that now. I think, as you can probably tell by the frequency with which I'm referring to the InstructGPT paper, the whole sub-area of instruction tuning and post-training is very closely tied to InstructGPT. So from the InstructGPT paper, you have equation 2, which is this objective that describes what we're optimizing. So we've got this r theta of x of y. This is our reward, and I'll define that in a moment. And then we've got these second terms, the log ratio of my RL policy divided by my SFT output. So what is this object? This is the KL divergence between my RL policy and my original SFT model. So it's saying when I do RL, don't move too far from where I started. And then this second line, this gamma term, this is basically saying keep doing pre-training while you do RL, so you don't catastrophically forget if you keep doing this. Lots of people don't do the second step, but this KL thing is a really, it's a standard thing. It remains even today. Okay, so now what is the reward? The reward is this thing kind of at the very top. And so maybe that's a small equation, so I'll talk through what that is, right? So there is a sort of hypothesized model of the world that exists. So what is the hypothesized model of the world? It's that every single output in the world, right, like that a language model could output, every single sequence has a scalar value r associated with it, and we don't observe what that r is. And when a person rates it, like when they do a pairwise rating of A versus B, what they do is they compare the two rewards of those two sequences, and based on the difference, they'll take a coin flip, right? So this is a logistic model of the difference of the two rewards. So every sequence has a reward. When I do pairwise comparisons, I take the difference and I flip a coin, right? This is the Bradley-Terry model of human preferences, and this is what's happening. And so when we want to optimize the reward, what we're trying to do is we want to output sort of the sequence that has the highest R. And R is not something we observe. We only observe noisy pairwise comparisons through R theta, right? So that's what we do. So that's the objective, right? So that's what we're trying to optimize. And so now let's talk about the how. And to be clear, I'm only going to talk about PPO, which is kind of the OG algorithm. This is what appears in InstructGPT and a lot of the OpenAI stuff. I'm going to talk about it only very briefly. And then I'll talk about it in much more detail on Thursday because it more naturally belongs there. We're going to do a lot more sort of real RL on that lecture. So at a conceptual level, remember what we want to do is we want to optimize the reward of some policy, right? That's the left term here. And what's a good way of optimizing something? Well, let's take some gradients, right? Let's take gradient descent. So that's the very top left equation here. Now, we can sort of do a little bit of math, and if we take the gradient of this object, we can write down that this is equivalent to the expectation of the reward multiplied by the gradient of p theta. And so this is very natural. What you're doing is you take your normal gradients that you normally take in doing like pre-training or whatever. This is saying p theta of z. I want to maximize that probability. And I maximize or I multiply that with r. So if my rewards are positive, I want to upweight those probabilities. If my rewards are negative, I want to downweight those probabilities, right? This is the policy gradient theorem. This is reinforced. You know, if you've taken RL class or something like it, you've definitely seen this before. Now, what is PPO? PPO, I think, is normally a very intimidating object, but I think it is actually quite simple. So there's two steps that happen. First, instead of taking a reward, we look at what's called an advantage. An advantage, you know, just to sort of gloss over a lot of the details involved, an advantage is basically a variance-reduced version of the reward. You know, if you go through the math, you can notice that I can subtract any constant, or in fact, I can subtract any sort of state-dependent variable from R, and this gradient will still be correct. That means that I can rewrite this reward potentially as sort of after subtracting any baseline values that I want. And let's say we call that the advantage. Now, not only that, maybe I want to take multiple gradient steps after sampling from p theta once, what's called essentially you know, sampling from one rollout and going almost off policy. To enable that, I have to essentially have importance weighting corrections, because the more steps I take, sort of the more stale my original samples become. And so this is what's called TRPO. You basically make corrections for all the gradient steps you take, and then you constrain yourself to stay close. Now, PPO takes the final step and says, instead of explicitly constraining myself to stay close to my old policy using this KL constraint, maybe what I can do is I can just clip the probability ratios, and this will naturally incentivize the model to stay close to the original policy. So this is kind of PPO in one slide. I'm not going to go into this with too much more detail, because actually this won't be the primary algorithm that I want to sort of just go through the rest of the lecture with. So at least in kind of the open research space and the academic space, a lot of the question that I think people were concerned with was, can we get rid of PPO? We will see this theme on Thursday as well. PPO is very complicated, and we have debated but decided against having you implement PPO because it will be suffering. And so lots of people thought, can we get rid of PPO? And they tried other reasonable things. And I will explain those reasonable things, like, you know, maybe we can SFT on the pairs, but for each of the pairs, we can prepend like a good token for the chosen good outputs and bad token to the chosen the bad outputs. And then I can just condition on good when I generate. That does not work very well. I can train the model only on the preferred output. That also does not work super well. I can use a reward model, sample the best one out of those, and then train on those. That works okay, but maybe not that great. And so people tried all these variants, but what really stuck was basically DPO. And I think the reason why it caught on as much as it did was because it, you know, removed a lot of the complexity of PPO and worked relatively well. And so you get rid of the reward model that exists in PPO. This is used to calculate the advantage. We get rid of any of the on-policy stuff, like the importance ratio thing that I was talking about. You just get rid of all of those. Instead, you know, we go back to the basics. We take gradient steps on the log loss of good things, and then we take negative gradient steps on log losses of bad stuff, right? We go back to very simple basic things. And the last part of what I want to talk about today is just deriving the DPO formula, right? So what is our goal? Our goal is to optimize this quantity at the very top. This is just a rewriting of that instruct GPT equation. I have a reward at the very front, and then I have a KL divergence. Like this keeps me, this is pi theta, close to my reference, right? So this is very natural. So the first thing I'm going to do is I'm going to assume that my policy pi theta is not actually a neural network. I'm going to assume it's an arbitrary function of any kind. And if I do that, then I can sort of write down essentially what the optimal policy looks like. It has this form. It's the exponential of the reward, and it's multiplying pi ref, the reference distribution over here. We can solve for the implied reward by solving for Rxy. And the clever part about DPO is now to say, okay, it basically means that every policy, instead of thinking about policies, I can think about rewards, because the two are one and the same under this non-parametric assumption. And so what you do is, remember, I have these two pieces. The left side This is the Bradley-Terry equation from the Stianon paper, the one before InstructGPT. And on the right side, this is the DPO sort of equivalence I wrote down. And then now what I can do is I can plug in these rewards R into this objective, and I can minimize this loss. I can say what I want to do is now I want to find a policy such that the implied reward for that policy has the highest probability of generating my pairwise comparisons, right? So now I've taken an RL problem and I have turned it into a maximum likelihood problem, a problem that's very much similar conceptually to something like pre-training, right? All we're doing is maximizing the probabilities, except what we're doing here is we're maximizing the probabilities of the pairwise comparisons, right? So those are the key steps. Start by making the non-parametric assumptions, parameterize the reward via the policy, and then optimize it using the supervised losses. I think we're a few minutes over, so we'll stop here. I think this is a good place because we got through the derivation of DPO, and we'll get through the rest of RLHF at the start of next lecture. Thanks everyone for asking lots of good questions.